So first of all of the code that is available that can reproduce the pictures and the videos in this talk is available on our GitHub website. So, okay. So first, I'll just start off with the people that do the actual work here. So this whole endeavor started when Dan Messenger was a graduate student with me. He graduated to being a postdoc with me, and then graduated to being a collaborator. And so this is something where he's been there since the beginning on this stuff. And let's see. So April is a graduate student. Seth is a graduate student. Vanya Dukic is a faculty in our department. She's a computational statistician, Bayesian statistician. And then we have three postdocs, Nora, Rainey, and Christian. And then there's some other postdoc and other graduate students who are joint with other faculty like Vanya and other people on campus. Okay. Um, what I want to uh, start off communicating here is that there is really two concepts that have guided a lot of where we've gone with our approach. And the idea can be really best seen just using a logistic difference equation, just to sort of demonstrate what I'm talking about. So this is, of course, logistic. It saturates, starts low, and goes up high. And we know the analytical solution is not terribly interesting um, separate variables. But the point is that for a model like this, if you want to estimate parameters like R or carrying capacity kappa or the initial condition, of course, and how do I say this? Basically, since the dawn of computational science, the dominant way we have done this, solve the equation, and either we know the solution or we have a numerical approximation to it. And then we, of course, compare with data. And maybe those six data points, maybe you have 100, whatever. But the idea is that we are, in essence, solving a nonlinear optimization problem via either solving the solution. Is that working better? Okay. Okay. So the point is that in order to match the solution to the data, there is a significant amount of effort with a lot of moving pieces, lots of hyperparameters. People make their careers solving PDEs of a variety of complexity. And what I'm going to claim here is if I look at this differential equation here, it is actually linear in the parameters. And what I want to do is I don't want to go away from the fact that we have a problem here, which is linear in these coefficients. And of course, I'm going to take the data and I'm going to substitute it into this problem. Now, there's lots of interesting things that are going on when I try to do that. But at the end of the day, that's what I want to do. So, what I want to use as my metric for identification of coefficients, identification of whatever as a part of this equation is I'm going to be looking at the equation residual, which is, of course, the left side minus the right side. And I don't want to get away from my linear solve, so linear problem here. So that's sort of the core. So step one is to think about substitution of the data into the equation. Step two is, of course, how do we deal with noisy data going into that time derivative on the left? Or, of course, if you have partial differential equations, all sorts of other interesting terms. And the way we're going to do that is by using the weak form. Now, the idea of multiplying by what we now call a test function and integrating by parts to pull the derivative off of the data itself, this has actually been around for quite a while. But at the end of the day, there were simply certain advances in numerical functional analysis, statistics, functional and numerical analysis, and numerical linear algebra that were not available in the 1950s and 60s. And so what I'm going to advocate for is that we kind of return to this idea of substituting the data in, but substitute the data into the weak form. And then we will be able to do parameter estimation, equation learning on multiple scales, of course, but that's simply one of the applications. So without further ado, let me go and talk about where this all comes together. So of course goes back to the 50s. The whole idea of plugging data into the equation and solving for the parameters is actually in the aerospace industry. They were trying to deal with these newfangled jet engines and how do you estimate parameters for your aircraft. And you basically just plug the data in. And the idea is you have a bunch of features, F1 or functions. These could be nonlinear, and F1 to Fk, and then you have time points 1 to m, and you simply plug them in and create this big matrix. And now you can go about identifying your W, which is these linearly linear coefficients here, because now you have to just figure out how to approximate the time derivative for the data, and this all works as a very straightforward regression problem. It's known as equation error least squares. It is incredibly fast, of course, because you're just solving the normal equations, but of course it's very sensitive to noise. And fast and sort of advances in solution error, output error, how do you solve the equation? This particular approach was discarded many years ago for more looking at the solution to the equation. All right, so fast forward to 2016 with the sparse identification of nonlinear dynamics paper. And so what Steve Brunton, Josh Proctor, and Nathan Kutz's sort of contribution here, which was really quite compelling and clever, was that they took that right-hand side that had all of our potential terms in there. It wasn't that we knew the model, so this is a large library of terms. And the idea is to set up exactly the same kind of regression problem where you plug the data in and you're wanting to minimize this equation residual, but it's going to be a sparse regression. So the idea, just simplistically, if this is what you're trying to identify and you want it to be the diffusion equation, or you believe your data is coming from a diffusion equation, the W you should identify sparsely should be 0 in the first entry, 0 in the second entry, non-zero in the third entry, of course, and then everything else is 0. Now, the idea is that given this large library of terms, we're going to add some sort of a penalty to reduce the number of terms, and we'll get eventually the sparsification of this to give us the true model. There's lots of assumptions in this, of course, because you're assuming that the library you have actually includes the model that you need in there. But that's those sort of different issues. The challenge, of course, and they admit this in the original paper and subsequent papers that followed, is that noisy data, this is going to be a problem. Taking two derivatives of noisy data, you have to be very clever about it. And if you do a very simple, just finite difference operation, you're going to, it's going to be scaling, the error is going to be scaling with the variance in the numerator and the step size in the denominator. So this is going to be a problem. Moreover, if you're trying to use this for, say, shockwave, equations that have shockwaves, this is also going to be a problem because you'll see discontinuities. So your true solution may not be smooth. And so how do you deal with these? This is where we come into the equation. So Dan is a graduate student. This was basically his dissertation, is we started considering the weak form of these equations. So you sort of change this into a multi-index notation. So the idea is this is basically your time derivative on the left. And you have to choose your test function cleverly so that you pull your test function off the data, put it on the derivative on both sides. But again, you're setting up a regression problem. And so this is incredibly fast to do now because you're simply solving least squares. So test functions look like these things. So we chose them to be piecewise polynomials. In some cases, we've chosen them to be C infinity bump functions. But the whole idea is you have something that is 0 at the endpoints. You don't have to worry about those pesky evaluation terms and integration by parts. And this is a derivative of this, obviously. If you squint at the derivative here, you can kind of see, oh, this is actually a continuum analog of the negative of a finite difference operator. So you kind of flip it upside down and you can see, oh, it's taking the forward minus the backward steps for as you multiply this by your function and then integrate. So create a whole bunch of these, sprinkle them along your whatever domain. You sprinkle them along the domain. Each of these, the blue, the orange, the green, each of them creates a new row in your regression function, and that you can then solve. The natural and nice part about this is, of course, first off, you have to choose a lot of properties of your test function, but we'll get to that a little bit later. The nice part about this is that it's very straightforward to extend this to PDEs. And so the whole idea is if you have your piecewise polynomial of radius a and power p, you can just multiply them across a different space or time dimensions, and you get test functions that look like this. And this is like a sixth derivative in x and one derivative in time kind of idea. So just to sort of communicate exactly how this is all flowing together, and I like this picture that I made here because it actually shows you how we can actually do this on a GPU incredibly fast. So this is a Swift-Honenberg PDE, so this is just a snapshot of the data. You have what we call a feature layer where you have the data to the first power, second power, third power, fourth power, and then you add what is effectively a convolutional layer in a neural network, which is taking these test functions there's just the phi derivative in x, derivative in y, Laplacian and a bi-Laplacian. There's obviously more of these you can put in here. This is just to demonstrate. So you pass each of these features through every one of these layers, and that allows you to create a weak form regression here. That then you solve this, you can sparsify the W's, sort of zeroing things out, things you don't want there, and then you keep going to inference and sort of loop around continuously until you have satisfied whatever stopping criteria. And now you sort of take a step back and say, okay, what are my non-zero terms? And it will pop out with the weak form of the learned model, which in this case comes out as the Swift-Honenberg PD. The P here is just a polynomial that is the appropriate one. Okay. And the reason I like showing this is that in this way, it really actually starts to look like some sort of an interpretable AI, right? Because we understand every single step along this way. It's simply that we're going to exploit what is capable of a GPU using a lot of, PyTorch, for example. Okay. So how does this perform? And at the end of the day, I'm just going to show one PDE and one ODE example. It works amazingly well. I mean, you do this in MATLAB, and MATLAB is great at solving least squares problems. So we take a noisy Lorentz equation with 10% noise, and given a library of several hundred terms, it can reduce it down to less than 1% error in the parameters you get out, which is pretty nice that it's that fast. You don't have to solve the Lorentz equation here, and that's really where all the speed up is coming from. Is the fact that that's not a critical part of this. So how do you even compare with like forward solver based estimation for these problems? You can, of course, as I said, the PDEs, the test functions can be done in space and time, and so choose a very nice, difficult Kermode-Sivashinsky PDE, and we can go all the way up to 50% noise. And for several hundred experiments with several hundred potential candidate library terms, it will correctly infer, basically for all of the hundreds of examples we tried, they was able to correctly infer these three terms. It wasn't always perfect on the parameters, and there's some reasons for that I can get into later, but these are sort of technical considerations. So we can actually do a lot better than this 7% error or 30% on 100% noise. Okay. Basically the JCP paper from 4 years ago now, we went through a large number of very challenging PDEs. Nothing takes more than about 75 seconds on a standard laptop to discover these. And I point out the purple row here is Navier-Stokes. This is basically a 2 or 3 minute YouTube video of flow past a cylinder. And if you take the vorticity form of the Navier-Stokes and you can get it in 12 seconds, you can learn the Navier-Stokes equation. There's no noise in this case, but you can still do this. So, this seems to be going pretty fast. So again, how do you compare with trying to learn other PDEs? Whatever system you're using, be it a pin or symbolic regression, it's difficult to beat 12 seconds for Navier-Stokes on the speed of these things. Okay, so let's get into, given that as our background, that we have the idea of taking equations or a library, an equation with a library of terms, and plugging the data into the weak form of that equation. Let's see what we can do if we want to try to learn things on different scales. So let's start with some interacting particle systems. So, and I'm showing you this. This is just sort of the motivation of why we drifted toward looking at this. This is an example from wound healing. So what you have here on the left is a two-dimensional picture of cells, and each individual cell is, we're actually able to find the individual trajectories for the nuclei, and you can see them going from left to right as they fill in this artificially scraped off piece on the plate. And you can sort of collapse it to a one-dimensional wave. We were able to, even using, so back then we could derive a PDE that is basically a, advection equation, nonlinear advection. And it worked, and it was able to fit the data. But at the end of the day, it was not providing a lot of insight into any mechanisms that were going on, and it was very frustrating. So we sort of looked at this and we said, okay, well, if we have the actual particle trajectories, maybe there's something that we can do in terms of learning the rules that individual cells are obeying. And so first off, we started with the first order interacting particle system. So this is just a pretty standard McKean-Vlasov. So you have your K is your interaction potential, V is your sort of local potential, and then of course you have the diffusivity over here of the for the sigma. And so what we did with this was to effectively look at a changing of the scale. So we took histograms for all of these particles that were running around. And there's sort of some standard ways that you can do this. But the reason we did that was we took the histogram. So every time step has a histogram spatially of where the particles are. You can actually then take the weak form of that, and this will allow you to discover this mean field PDE, which has all of the things you care about, right? It's got the potentials in here. It has the diffusivity, basically the diffusion coefficients. And so what you do is if you run a bunch of particles, and we're going to look at the histograms of these particles. I think there's several thousand, maybe 4,000, I think 4,000 particles here that are all running around. And they have a variety of potentials and interactions and stuff. And let's see how this works. Oops. So just in general, for this case here, we need fewer particles, and because of the strategies we have for choosing the bin widths here, it's actually just not going to be a problem. And so this is now a histogram of the previous picture. And so this is now the data that is being fed into the weak form sparse identification of nonlinear dynamics algorithm. And doing this, we can now, given a set of libraries of terms, we can recover basically the red, blue, and brown terms. And there, I think this is a little bit small, but this is on the vertical axis here is the error in the learned interaction potential. This is the error in the diffusivity. And then along the horizontal axis, you see that basically we're obeying what you would expect theoretically. So this is the number of particles as you go along the horizontal axis, and blue to red to black is different numbers of experiments. And then the purple dotted line is just for reference, the root n, basically 1 over root n convergence. And it's sort of, you can see that, not always exactly working, but it's obeying pretty much a 1 over root n convergence here. So that's kind of nice to see that it's matching up with some theory there. So we didn't just stop with sort of these simple systems. We have the different types of interaction potentials. In this case, it was 0. We just have basically this local potential. But one of the things we did do is we started investigating spatially varying diffusivity. Okay, and that actually comes up. So we obviously get these Fokker-Planck equations. But what was really interesting was if we thought about this as looking at the sparsification, it actually identified the homogenized equation. And this is sort of a well-known theory that this omega bar that should come out is actually the harmonic mean of this. And it actually is able to recover the 0.62 without knowing all of the theory about how you go through and derive the homogenization. Okay, and so this is just sort of expanding this. So that as the number of particles go to infinity with this highly oscillatory PDE, you can get it will actually converge to this. The limit is giving you this homogenized equation, which is kind of interesting that it's this is basically just doing sparse regression, but we're able to derive something which is technically challenging to come about. And these are just pictures demonstrating this again with the sorry, I forget the order. This is the diffusivity. This is the local potential, and you can see as the number of particles goes up, you have this convergence that you expect. And this is actually for these higher and higher or oscillatory frequencies. It's not quite as great on the diffusivity part, but it's doing pretty good on the local potential. This one down here is sort of a measure of how accurate your recovery is for the term. It's TPR, total positivity rate. Basically, you want it to be 1, and that tells you that you are correctly recovering the equations. So as you get more and more particles, you're doing better and better at recovering the equation correctly. Okay, so what about a non-local example for the interaction potential? Turns out this one works pretty well. Also, we can identify these non-local interaction kernels, and the reason, and so these are just this is adding more and more noise, and of course, as you add more and more noise, you do worse and worse. And then also, of course, as you add more particles, it does better in roughly speaking, the matching the 1 over root n. convergence here. But in general, the whole point of what I'm trying to say here is that given trajectories for particles, we can take histograms of them and recover the mean field equations. So even if your model is starting on a small scale, we can recover these mean field equations, which, as you look at the parameters that are coming out of this, this may be exactly what you need is looking at the coefficients that are on the terms. So this is I'm hoping that there's some connections here that might be interesting with the upscaling and of the electrons. Um, we, of course, went a little bit further, did some non-local Keller-Siegel chemotaxis. It's the same story. Yes, of course, as the noise goes up, it gets worse and worse, but not quite that bad. I mean, we're talking, order one noise level is basically getting you roughly between 10 and 30% error in the interaction potential. And then, of course, things get better as you increase the number of experiments, even. So this is an experiment, number of experiments, and then these are the number of particles in your trajectories. Okay. Okay, so with that as the first order, we were very excited about that. But the problem was that the cells didn't seem to want to obey first order stochastic differential equations, or mean fields of that at all. And so we went back and we got some experiments to try to consider what would happen for second order equations. Now, there was some challenges with the data, and so what I'm going to present here is actually more of a modeling experiment. Because this was the first set of experiments that they gave us, and we tried to learn basically the adhesion repulsion potential, the alignment potential, and the drag. And sometimes we were able to do it pretty well. Sometimes it matched up with these are sort of all these little trajectories of the cells as they wiggle around. But at the end of the day, there was some problems with the experiments. They discovered there was other cells in there that weren't actually showing up on the nuclei, so we weren't able to really get a great prediction on everything. And so while they were redoing their experiment, we went back and we considered, all right, so what happens if we have artificial experiments? Like, let's come up with potentials and let's artificially choose potentials. There's alignment, there's attraction repulsion potential and alignment potential that match up with the sort of first pass we did. But let's see how good we can do if we have trajectory data like this picture here, just to show it collects together and then migrates. If we have those trajectories, can we learn these potentials from that? Oops. And so these were this, and to go further, since we knew we were going to have maybe some mixtures of cells, we said, okay, let's see if we have different species, artificial species, where maybe they both have alignment and attraction repulsion, or just attraction repulsion, or just alignment. And you can do pictures like this. So the gray spaghetti mass behind are the actual trajectories of all of these artificial cells. And this is a subset of the cells. The teal all have a same trajectory, or sorry, same model that they're coming from. And this is a no noise case. I'll fully admit that, but I think it's really striking how it can learn a model that is able to reproduce, a 90-degree turn followed by a 180-degree turn. So the black is the data curve, and the teal dashed line is the model prediction of this. And we're not even using all the data in the experiment here to learn these interaction potentials, or the potentials that are force potentials that are telling us how to go. So this, of course, naturally leads to let's learn the potentials for all of the individual particles, and that takes fractions of a second, and then we can go about sorting them. And it turns out just by looking at the noise or the error in your prediction based on the trajectory, you can actually sort them. It eventually ends up being a log normal distribution. You can split whether or not the model is correct. And this allows you to take this spaghetti mass of multicellular, multi-species trajectories and sort them into individual different species. And so, of course, this was the publication that was it was kind of exciting that we were able to basically sort these, passing it through the WSINDy algorithm. So it took a few years to get the experiment correct, but now there's an experiment that our collaborators in biochemistry have done where they take a 2D sheet of cells, and then you can see exactly they have scratched it down the middle and given it a growth factor, and now the cells are migrating into the wound. And so the idea here is there's in principle a kinship between this kind of a model where you're looking at individual cells and particles to see how the particles are moving. And it turns out that this second order interacting particle system model seems to work pretty well, assuming you have sufficient data. So this is the snapshot of the wound at different time points, and then you see this fingering happening as they move into the wound. And I'm going to zoom in just on this finger here, and we're going to look at cell 1798 with our standard traction, repulsion, alignment, and drag model. And we're going to zoom in here. So the red trajectory is the cellular movement trajectory, and our blue trajectory is the learned potentials. Now, this is really quite compelling and interesting. So, sort of if you look at the actual size, the black circle represents roughly the size of the cell. They're a little squishy, so this is an idealization of a hard cell. But the idea is that this is the attraction repulsion potential that this cell that our model has learned from this trajectory. And it's saying that I don't want to go ahead of you or behind you. I don't want to be too close to other cells, but left and right, it's okay to sort of join hands and march forward in a sort of a line. And this is kind of one of the things that we are seeing in some of the data. This picture here, this potential is showing you the alignment potential, which basically says for a cell that's moving in this picture, the upward direction, it cares about who is in front of it and what is the velocity of that cell in front of it, but it doesn't really care about what's going on behind. So one of the things that we did find that was absolutely critical is that in the set of library terms, it was essential that the potentials be allowed to have asymmetry. So it wasn't just a radially symmetric potential, but that it actually could create these structures of the potential surface such that it could repel forward and backwards and attract left and right, effectively, of the direction that the cell is moving. Also in full disclosure here, we can't learn the potentials for all the cells. We do really the best for cells that are interior because a lot of what we're doing is based upon interactions. And if the cells, say, are wandering off over here by themselves and they don't really interact with another cell while it's moving, we have difficulty learning these models. But you can see for like the red one is in the middle of the pack. There's a lot of interactions between this cell and its nearby cells, and so we can learn the models pretty effectively. Okay, so bringing this together to some other types of physics applications, I was unsure precisely how this would connect with the electron well, basically models there and multiscale, but I thought this would be relevant. So let me show you what we're doing here. So these come from plasma physics, and this is basically in we start with a 8-dimensional ODE model that comes from a Hamiltonian, and via careful choices of the reduced order model, like using WSINDy to create, say, a 4-dimensional submodel that has a free parameter in it that we can choose, we can actually choose the time scale that is being learned from the larger dimensional model. So this case here is there's these it's a subspace of your phase space of just these three variables here, and the black curve is there's two oscillation scales going on, right? There's two time scales. So you see a sort of a slow loop while it's wandering around, and then a fast loop where it's oscillating this way. And as we change the scale we want to learn, we can either learn the teal here, which is this sort of fast oscillation, or we can go all the way to learning the red model, which is the slow oscillation. So there's definitely some opportunity here for learning different models on different scales that you can prescribe. This is just for time scales, but there are some things we've had, some research we've done on looking, we haven't published anything on it, but looking at the different space scale models that we could choose. And this is when one of the things came out last year. The other said this is more of a trying to merge some of the weak form approaches with neural networks, and this is just looking at a surrogate model. where you have different parameters with the initial condition for width and amplitude, and trying to match it is using sort of trivial or simplistic reduced order models doesn't work really well, especially if there's noise. If you do just do the weak form of it and then learn the reduced order model using that, then you are able to, sorry, you're learning at the black squares is the parameter values you have trajectories on. And then you learn the reduced order model based on the weak form. You can get predictions at all these other points that are, basically the limit of your projection operation for the reduced order model. And so you get these great speed ups. Depending upon the data, one of these two approaches or the previous approach by looking at the interacting particle systems, that may be relevant for you. I mean, the whole idea is, you choose your scale and then it can give you the automated discovery of the model there. Okay, so those are sort of the applications. I wanted to bring up a few points that are basically idiosyncratic and specific to using a weak form equationnaire. So plug the data in and look at the weak form. And there's a few things that you need to be aware of if you want to do this that we have looked at. The first one is to do this regression problem is not a standard regression problem. Your noisy data is actually appearing both in the matrix that you create as well as the vector. And so if you do an ordinary least squares just to solve the normal equations, this will go poorly because this is actually a generalized least squares problem. So the pictorial demonstration of this is in ordinary least squares, you have errors that are just in the output, that B vector vertically. The problem is that you actually have a total least squares problem. So if you don't account for this and you just use the regression or the sparse regression, the coefficients that you get will be biased. They will, in essence, be wrong if you have noisy data. It's just this is very well known in statistics, and there's some really nice work that's happened over the years to correct for this. One of the ways to do this is use iterative reweighting, where you basically solve your equation, your ordinary least squares, and then you update the covariance matrix. Most of this is just bookkeeping, except for this part right here, which is looking at the Jacobian of the terms in your equation. So it is correcting the covariance to get rid of your problems in the estimate of W based upon the actual model itself. But this is just a first order expansion to do this. So there's more sophisticated ways to do it, but this is pretty critical. And you can see this just by using a simple, this is a kind of a stiff Fitz-Uniguma with a cubic in there. If you just use forward solve and try to match things, it's going to take you a really long time to do your, maybe hundreds of seconds, and your error is not going to be so good. Whereas if you use this iteratively weighting in our weak form estimation scheme, it's just regression, so it's really blazingly fast, and basically different noise realizations give you different values, but you're still doing much better than the forward solver. So don't worry about the green; that's not important here. One of the really awesome parts about using this particular approach is that you get uncertainty information about the parameters for free, in the sense that you're using a regression problem. And so you can compute the covariance matrix just directly if you know the noise structure. So if you know the noise structure of your data, or you can estimate it in a reasonably accurate way, you can then get the covariance information about your parameters, which is kind of cool. And oh, sorry, I forget if I mentioned this. So this is the situation where you know what the equation is. And so this is weak form estimation of nonlinear dynamics. So this is different than the WSINDy, which is discovering the equation. So, of course, one of the ways that we have thought about doing this is use WSINDy to discover your equations, and then you can correct your parameters using WENDy after you know the equations. Okay. Another direction that is really this is challenging, and we have only scratched the surface on this. Is one has to acknowledge the reality of experimental data. You never get every single state variable that you care about. And so, just preliminarily, we have an effort to look at just in ODEs. What if you say only measure? I mean, we all know what an SIR model is now from epidemiology. This is pretty, past few years have taught us this pretty well. So the idea is, of course, what if you can only measure like the number of people in the hospital? Or you don't really get susceptible or recovered. And so the idea is to use some differential algebra techniques to collapse this to a single differential equation just in I. And it turns out you can still do your parameter estimation. And so this is for a nice, just a simple academic here with noisy data. You can get really great estimates here Uh, sometimes it's in this case it ends up being comparable for some of the forward solver based ones in terms of the parameter estimate. But one of the important things to keep in mind is that as you increase the noise level, forward solver based problems are highly dependent upon giving it a wise initial guess for your problem. And so this picture here, yeah, there's a few cases where the noise realizations you're able to do better with the forward solve, but this is actually only 40% of the experiments we did. 60% of the experiments failed completely for a large number of initial guesses on the parameters, whereas this is 100% of the experiments, and they're fairly predictable in terms of how long they take. So, um, one of the other directions that we've thought of going with is trying to estimate the parameters in case it's not a linear equation. So normally we want it to just have these parameters be coefficients. If you happen to have a parameter in the denominator, turns out you can set up a maximum likelihood estimation problem, and this works incredibly well also. So this is obviously just in a preprint right now. But if people are interested in sort of nonlinear optimization estimation of the parameters, we can now do that as well. And sort of, course, bringing it all together, we want to do for PDEs. And so let's go back to our Kermode-Sibishinsky. Let's noise it up, and we want to infer the parameters that are, all minus ones. Turns out this is sort of what we're working on right now. This is amazingly fast, right? Because we don't have to solve the PDE, and that's Kermode-Sibishinsky is spatiotemporal chaos, so it's very challenging if you guess parameters that are wrong or if it wanders off into a place where the parameters are giving you even worse dynamics. This is going to work a lot better, this weak form approach. And this is the wall time versus the relative error here. Okay. Um, the one nice thing about the weak form that we've been working on is it lends itself in a very straightforward way to thinking about theory. It wasn't easy to do this, but actually, I want to make sure I get through all this. But basically, we have a theorem that says, the SINDy problem of equation discovery does converge in the limit of of getting enough data, this n value here. Now, it's interesting. There are some restrictions on this. This theorem that we have in this IMA numerical analysis paper that came out in December, it's basically we limited ourselves to a certain class of noise, which is basically something that is dominated by a Gaussian, so sub-Gaussian noise. We limited ourselves to libraries, which were polynomials and trigonometry terms, which it covers, a significant fraction of mathematical physics. And so the idea being that there's a critical noise level, and as long as you're below that noise level, this is basically saying the way in which, with probability one, you will discover the correct PDE, or the just correct differential equation. The visual demonstration of this is that for this, this is kind of it's like a hyper Kermode-Sibishinsky. It's really quite sixth derivatives and other things. This is the solution numerically. And this is kind of what the test functions are, the sort of the contour, what it looks like, just a little, that type of a radius. And over here, you can see along the horizontal axis is more and more data. Along the vertical axis is basically the probability of correct recovery of the equation. And as you can see, as the noise gets larger and larger and larger, this is saying that we're still below that threshold. As the noise goes up and up and up, we're still able to converge to, with probability one, get the correct model. And this actually led to us coming up with the conclusion about discoverability classes. So if you have a model, there's certain classes of equations where if that's what's really going on, it doesn't matter how much noise you have in the limit of continuum data, you will be able to recover the correct equation asymptotically. And it turns out the biggest thing is it has to be order two or less. And so to sort of see the full, I don't want to go too much into the theory here, but this is it's all laid out in there in terms of what's actually the limit of discoverability there. Okay. Um, let's see. So, sort of just the summary here. So we have for this weak form scientific machine learning, we don't have, all of the tools in the toolbox that scientific machine learning has, but what we do have is we're building a fairly complete set of equation learning and parameter inference set up here. All the code is available in a variety of languages on the website here. The MATLAB and Python. The Python one actually has some extensions where you can run it on GPUs using PyTorch, and usually because setting up that matrix is the largest, sorry, that matrix G in the regression problem is the largest sort of time-intensive part. You can actually accelerate things by an order of magnitude if you just write it in PyTorch, and it'll do it on the GPU quite nicely. Um, One of the other things that I did want to sort of mention here is that there has started to develop an ecosystem and an awareness that this is really a compelling way to do things. And these are sort of other groups that have been using weak form versions of things that are built off our stuff. Now, I mean, I will say the full history of this. Sorry, I'll get to that in just a second. But basically, and they have various, using an ensembling, using different mixed integer optimizations. So there's a lot of extensions that are directions we didn't think of going that have been quite interesting that people have thought of. So just to sort of acknowledge the people that are doing this. So we of course have some funding from a variety of agencies. These are the people who are currently working on the project that I mentioned early on. And then I wanted to draw your attention to two particular articles here. So we had a SciM News article back in October of last year that talked about a lot of these methods. If you're looking for a little more technical overview, there's a chapter in this Handbook of Numerical Analysis book that came out earlier in 2024. Um, and there's actually in the SciM News article, we have a link to an archive preprint that we put up that really describes the history and the background of this. And at the end of the day, there was an awareness that SINDy itself had issues with noise. Even if you tried to compute regularized derivatives, it was still not exactly giving you what you wanted in many cases. And about the same time, in that 2019 to 2021 time period, there was actually four groups that all hit upon the same weak form idea. It was Roman Grigoriev in physics at Georgia Tech. There was not Bertsimus, sorry, Simarindos, and who was a machine learning person over in Europe. There was Garikapati at Michigan in engineering, and then us that sort of all came together. And each of the groups have very different points of view. And this is sort of outlined in the archive preprint that's linked off this SciM News article. That like Derek Kapati was coming from a chemical engineering background, and he was very much using a lot of the finite element toolbox and code that they have developed over the years. And Grigoriev was looking at it from a physics point of view. And so they've done some really nice work on I think the acronym is SPIDER that they're using, where they're restricting it to symmetric or basically symmetric operators. So it's more of a physics restricted idea, but it's still using these weak form and sparse regression ideas to discover equations. And then the machine learning people, actually, this was the only paper they did on this, so they've moved on. But each both Garikapati and Grigoriev have extended in their own areas in this. So that's why we're kind of excited, because it's sort of there's this consensus that looking at the weak form is really quite helpful for dealing with real data here. Now, from our point of view, of course, we've been looking at this from an applied math and math biology, and even in some plasma physics examples. And so this has been useful for us as an area for us to look at. But I will say, sort of, if you're looking for, and these are just the preprints that just came out recently. I will say, if you're looking at getting into this, the SciM News article is really the best overview to start. And then the handbook is sort of the technical introduction to look at. And then, of course, these are the first two, the ODE and PDE models PDE papers that started the whole thing. And then the parameter estimation when we figured out the totally squares and the correction for the covariances. And then a variety of other papers that sort of supplement this. I did want to draw attention to the last three here, which are currently bouncing around in review. That sort of Nora's paper on looking at identifiability and when you have hidden compartments. and then Rainey's paper on some, discovering structured populations, and then April is a grad student who has really nicely come up with a way to look at how do you actually choose the test functions so that they give you the answers that you want. I guess I talked a little bit fast, but anyway, that's the talk. Thank you.